So, as we are discussing about the static routing protocols in the last class, and we studied about the Dijkstra algorithm, the shortest path routing algorithm, where the algorithm finds the shortest path between any source and and the destination by calculating the cost associated with each path and comparing that and is selecting working node in between the sender or the transmitter and the receiver, and a path is established statically. Coming to the next kind of a static routing algorithm or a non-adaptive kind of routing algorithm is flooding. You must have heard this term flooding. What flooding is? Flooding is a kind of routing where every router, when I say about a node means it is working as a router now. Every router when receives a packet from an incoming path forwards the packet to all other paths which are outward. That means a packet when received by a router is forwarded to every other path connected to it except the one from which it has received. So, imagine we have if you have a topology like this, if A is the source, then initially if the packet 1 is forwarded, A forwards to B, A also forwards to C. Then let us say P1. So, P1 is a packet now received by B, also received by C, P1, here also P1. Now, what B does after receiving from A, it forwards the packet to D, let us say here is D. So, now P1 comes here, and similarly C after receiving P1 forwards it to E. So, now P1 comes here. Now, E when receives the P1 from C, the same P1 it forwards to D when it receives from C, and again E when receives the P1 from D, it forwards it to C, and when the same packet P1 comes from E to C, this is again forwarded back to A. That means, if you see, the flooding results into a loop, or you can say the infinitive forwarding of the packets when there is no end to it. The strength of this one is, what could be the positive strength of this kind of algorithm? Flooding, reliability. The number of packets are so much that at least any receiver is expected to receive a packet from the other one. So, usually in the defense or in many military field, this kind of protocol or routing is preferred. But the drawback is, if this is the strength, what is the drawback of that? Is the bandwidth consumption. Same packet being forwarded multiple times with any link consumes the bandwidth, so the throughput of the transmission or communication is degraded. That is what is the flooding. But keeping the strength of flooding, if you want to have a really efficient flooding of the packets, how we can damp the number of or repeated forwarding of the same packet. So, one of the method of damping this infinitive forwarding is by adding a sequence number, to every packet. So, when the node A, let us say the node A starts the packet or generates the packet, what it does, in the header field it adds up a sequence number, let us say n, and it puts let us say n is the sequence number, fine, and the source ID of A is, the packet is A. Now, this packet is forwarded to node C and node B. So, what the node C and B does, they make a list of the packets they are receiving from the source. So, what they enlist here, from A they have received a packet which is of sequence number n, right. So, next time by any other means, if the same packet comes to it, let us say same n comes to B for forwarding, what B does, it checks for the list, and in the list it finds that the sequence number n with the same source A has already been forwarded. So, what it does, instead of forwarding the packet again, it simply drops the packet. So, your number of forwarding of the packets or number of flooding of the packets into the network is reduced if you give an sequence number along with the source ID to every packet. Another is, in the packet you include a field called age. This age defines how many hops a packet can visit. Let us say you say the packet can visit 100 nodes, the age of the packet is 100. So, every time the packet visits a node, the age is reduced by or decreased by 1, and finally, when the age reaches to 0, the packet is dropped. That is another way of damping the flooding or reducing the number of flooding packets in the network. But how do you know this age? How a node selects the number of hops that could be visited by the packet. So, in the worst case scenario, what it does, it considers the whole of the topology of the network. Let us say it understands that my network, or I am a node in the network whose number of nodes or the total dimension is, let us say 100. Then in that case it can put a age of 100. But knowing the dimension of the subnet by any node is a very difficult task. So, either they can go for a higher number as much as possible, or they can, if they have any provision to understand the number of nodes present in the subnet, they can give the age accordingly, and this could be done. So, either by adding a sequence number along with the source ID, or by incorporating the age of a packet, your number of flooding could be reduced and your reliability is achieved at the same time. Another third option is, if this is the first and this is the second option, then another third option is called selective flooding. What selective flooding says, if a node understands the location of itself, it must know the location of its neighbor as well. Which nodes are to the east, which nodes are to the north, or any other direction. So, what it does, instead of forwarding the packets in every direction, it can forward in only one direction. So, whoever will be the nodes in that direction will receive, and they can further forward if the location is known to the node. So, you can say also this is a kind of location aware routing protocol. If he knows its location and the location of the destination as well, instead of forwarding it in every direction, it forwards towards the direction of the destination, and finally it is received by the destination. So, this is also a kind of static algorithm, the flooding, and how you can check the flooding in order to achieve the reliability, maximize the reliability and minimize the bandwidth consumption. So, these are the two very important kind of static routing algorithms that we will cover, and next to this we will go for your dynamic routing algorithm. So, next is your dynamic or the adaptive routing algorithm. As we discussed in the last class, in this kind of routing algorithm, every router decides the next hop depending on the network scenario. How the network scenario is decided and how often the scenario is studied. Let us say if A and B are two nodes or the routers, and currently the traffic in this channel or this connection is the order of, let us say 100, and the next t second the traffic goes to the order of 200. Is it wise for A to send the packet again in this direction? Definitely no. So, what it does, it again finds another path if it has any alternate path through which it can send the packet. That means every routing algorithm which is distributed in nature executes the routing algorithm to decide which path I should follow at this point of time to forward my packet. That is why we say this is non-adaptive. Sorry, this is adaptive. And in this category of routing algorithm, the two very important routing algorithms that we will study is the distance vector also called the Bellman-Ford algorithm. And this algorithm is more popularly known as Bellman-Ford than in distance vector. You will find even every wireless routing protocol today also they apply the principle of Bellman-Ford algorithm for finding the path, because this is the adaptive one. So, depending on the change in the scenario, they can change the routing algorithm, they can change the path to forward the packet. And another very popular routing algorithm is link state algorithm. So, your distance vector and the link state routing algorithm, which are the dynamic kind of routing algorithm, we will see one of them, we will see both of them. First we will go for the distance vector or the Bellman-Ford algorithm. What this Bellman-Ford algorithm does in a network topology, every node maintains a specific table called the routing table. So, if A has a routing table of its own, D2 has got its own routing table and C2 has got its own routing table. So, every node has got its own routing table, and this routing table contains, other than the other informations, two major informations. One is the what this routing table actually contains, it contains the path to every destination in the subnet. So, if you have how many nodes? 1, 2, 3, 4, 5, 6 nodes, then it has got 6 entries for A, B, C, D, E and F. So, A has got an entry for all the destinations saying what is the cost to reach that destination and what is the preferred path for that. So, these two entries are, you can say, one is the cost, another is the preferred path. When you say the cost associated to reach, cost means it could be your number of hops, it could be your distance, it could be any other factor. And preferred path means to reach it that next destination, who is my next hop. Because what is the job of a routing algorithm? Any router, when receives the packet, it has to deliver the packet to its neighbor. And if it has multiple neighbors, who should be the preferred neighbor to whom I should deliver the packet, and that is the preferred path. If it sends to any destination or the neighbor who is having a longer path to the destination, then there is no point in choosing the algorithm. So, always preferred path means who is the best next path to whom the router should deliver the packet for further forwarding. Now, if you say this, if I have a topology, let us say I will say 4, 5, 6, 9, 1, 2, right. So, A, to reach at A, what should be the cost? If A is the source and A is the destination, what is the cost of reaching to A? The cost is 0. And who is the preferred path? A himself. Right? Now, to reach at B, if A wants to forward the packet to B, it has two paths. One path is directly from A to B, another path is from A to F and F to B, right. So, two paths, and what is the cost of each path? One path cost 4, another path cost 6 plus 1, 7. So, which should be the preferred path now? This one obviously A to B directly, right, and what is the cost associated with that? So, the cost is 4, and to reach at B, the next hop is B itself. Now, to reach at C from A, find out the path. One is A to B plus B to C, that is 4 plus 5 is 9, one path is 9. Another is A to F, F to B, B to C, 6 plus 1 plus 5 is 12. And another is A to F to C. So, A 6 plus 2 is 8. So, which is the lowest cost? Definitely it is 8, and who is the preferred path then? To reach at C, I am sorry, any question? A wants to reach to C. One path is A to B to C, that is 4 plus 5 is 9. Another is A to F to B to C, right. So, 6 plus 1 plus is 7 plus 5 is 12. Another is 6 plus 2 is 8. Another of course is there 9 plus 2 plus 1. A, B? Okay, A, B, F, C, yes, correct. 4 plus 1, 5 plus 2 is 7. Now, tell me which is the best path now? Lowest cost? Definitely this one is 7. And who is the preferred path now? B. Correct? So, similarly to every destination, it is found that there is a cost associated with that, and who is my best neighbor to that. This is what is the table of A. Now, once A finalizes its table, what it does, it exchanges the table with its neighbor, and who are the neighbors? B and F, correct? And they have already their own table existing with them. B has its own, F has its own table, B has its own table, and they have found the path accordingly. A, B, C, D, E and F. They have their own routing table. Similarly, F2 has got the same A, B, C, D, E and F. Right? Now, A has its own table, B has its own table, F2 has its own table, and with a certain interval of delta t, what they do, they exchange the tables in between. The neighbors, they exchange the table in between. The reason of exchanging the table is if f finds any path to reach to C, let us say f initially has a path to reach to C is 30, let us say, and the destination is E, I mean the preferred path is E. But when it receives the table of A, it finds that A can reach to C with a cost of 7, but I can reach to C with a cost of 30. If I can reach to A, C can reach to A with F can reach to A with a cost of 6. So, if I can reach to A with a cost of 6 and 6 plus 7 will be 13, that means if I change my path via A, I can reach to C with a lower value which is equal to 13 and the preferred path will be A. That is the objective of exchanging the tables between the routers to get the updated values and update their routing table accordingly, right. And this is the reason why it is called a distance vector algorithm. Everyone has got a vector which identifies the distance to the other nodes, and this distance vector is exchanged between the nodes to find out the updated value. Now again, this is one point that why they exchange the routing tables. Now how they calculate the cost associated with the link? It may happen that if the cost is now 7, the next moment the cost could be 9. By sending any pulse or impulse signal or any beacon, they can calculate what is the signal link cost. And if the link cost is updated, they first update their own routing table and then the updated routing table is exchanged with the other nodes. That means there is a local update, there is a global update. Both the cases takes place in case of the distance vector routing algorithm. The local update finds the path to each of its neighbor, update its own table. Then once the local update is happened or over, it has to be exchanged with the other nodes so that they can also update their table according to this table. That is what is your distance vector routing algorithm. Now, let us work out an example on this. Let us say you have a topology like this, you have 9 nodes, let us say. I have 3 nodes here, 3 nodes. My topology is like this. A, B, C, D, E, F, G, H and I. Let us consider a node H. Let us consider a node H whose table is, I am just giving only those 2 fields, I am not considering the other fields. So, for this is the routing table for H. A, B, C, D, E, F, G, H, I. This is the current value of H, forget the preferred paths, we are not considering that now for this example, right. And at time t1, H understands that the tables associated with, so H will receive the tables from which other nodes? One will be G, then I, then E, then D, right, and they have their own routing tables. So, let us say G and I, we are considering only this G and I, okay. Let me give this one also, 13, 5, 16, 9, 18, 2, 13, A, B, C, D, E, F, G, H, I. Sorry, this one will be, I will be 0 here, this will be 0, G will be 0 here, and E will be A, B, C, D, E will be 0 here, and this will be 0, rest you take any random value, A, B, C, D, E, F, G, H, I. So, these are the tables associated with the neighbors, right. Now, at point T1, H understands that I can reach to G with a value of, what is the earlier value? As 21. So, now I can reach with 15. I can reach to D with a value of 8. I can reach to E with a value of 6, and I can reach to I with a value of 5, right. Now, update the local table of H, find the updated routing table of H at time T1, do it. What will be the local updation of the routing table at node H when it understands or it learns that the new updates for its links to its neighbor nodes are this, and the table of the neighbor nodes are as given to you for G, I, E and D. With this, find out the updated table for H. So, the new table for H should be here. This is for A, this is for, sorry, H. Tell me what will be the updated table now. By using the distance vector routing algorithm. So, I do it for you for this value. Rest of the values you find out and tell me. Tell me for A, H wants to reach to A. So, what is the updated value to reach at A? 3. So, she finds H can reach to A with a value of 3. Let us find out. Who is the neighbor of H? first is G, right. So, cost is 15 and G to A is 5, right. So, if I go through G, then it will be 15 plus 5, which is equal to 20. Now, if if H goes through I, what is the new value? Is 5, and in I stable to A it is 13. So, 5 plus 13 is 18. If H goes through D, then new value is 8, and in D stable, what is the value to 1? 8 plus 1 is equal to 9. And if H goes via E, then the cost is 6, and in the E stable, the value is 11. 6 plus 11 is 17. So, which is the lowest value now in the updated study? Definitely 9 is the lowest cost. So, now if H wants to reach to A, the new cost is 9, and who is the preferred path? D. Is that clear? What is my next neighbor cost, the updated neighbor cost, and in that neighbor what is the stored value, and it decides what is the update for the current table. Similarly, find out for B. Anybody who could found for B? I am sorry, 7. So, H to B new value is 7. Let us see. So, if H goes via G, this is 15, and in G stable it is 10, right. So, this is equal to 25 if it goes via G. If it goes via D, then value is 8. And in the D stable, what is the value for B? Is 2. 8 plus 2 is 10. And if it goes via E, the value is 6 plus, in the E stable it is 13. 6 plus 13 is 19. And if it goes via I, in the I stable B is 21. 5 plus 21 is 26. So, definitely which is the value? So, next value is 10 for B, and who is the preferred path? Again it is D. Is that clear or still in doubt? Any doubt? Find out for C. Tell me at least the correct value for C and its preferred path. That means if I give you any packet to deliver it somewhere, I am sure no one of you are going to get the best route. 11? This time correct? Let us see. So, H and C says it is 11. Let us find out. So, if it routes the packet via G, it is 15. 15 plus how much? In G it is 21. So, this is equal to how much? 36. And via D it is 8 plus, in D stable it is 15. So, this is equal to 23, and in E stable it is 6 plus 5, that is equal to 11. Then in D stable, I stable it is 5 plus 8, that is equal to 13. So, the next is now 11, the preferred path is. So, now only she got the right path to route the packet, correct. So, rest are still confused in the subnet how to deliver the packet. Find out for D. I need one more correct answer, not from you, not for you, anybody else. Who can give me the correct answer? 8, 8E, E, D for Delhi. So, C says H and D, the girls can do better routing then. Okay. So, let us see H and D, this will be 15 plus, in G's table the D is 3, which is equal to 18, and in D's table it is 8 plus 0. Oh, you are lucky then. This is not accepted. So, D is the immediate neighbor, not possible. E is the immediate neighbor, not possible. D, E, F, find out for F. The value is already studied, so you did not calculate anything. Give me for the path for F. 8, for F it is 8, H to F it is 8, correct? Let us find out. So, if I go via G, it is 15 plus in G's table, F is 8, that is equal to 23. If it goes via D, then it is 8 plus, in D's table F is A, B, C, D, E, F, 9, that is equal to 17. And if it goes via E, this is equal to 6 plus E's table A, B, C, D, E, F, 18, which is equal to 24. And if it goes via I, this is equal to 5 plus I's table A, B, C, D, E, F. Oh great, this is 8, right. So, the new updated value for reaching F is 8 and the preferred path is, right. So, in the similar way, D is equal to 8 as given, E is equal to 6 given, G is 15 given, and I is given 5. I am sorry, who is 15? No, cannot be, because that is the newest value. That is the latest value that has been updated. So, maybe the traffic has been increased, maybe the cost has been enhanced. So, that updated value, it is not like shortest path, you cannot overlap that. So, that is the new current scenario of the topology that has been studied as 15, though it was less earlier, but now it has been increased. So, we cannot replace that. So, with this new value, may be increased or may be decreased, you have to find the next local update of the current table, which is the now table for node H, correct. So, once this table for node H is updated, this will be now exchanged with E, D, G and I, and they update their table accordingly, because they may have to again route through H. So, every node that may have a possibility through route through H, they will update their table, and again their neighbors will update. So, accordingly there will occur a global updation of the routing table in the whole network or whole subnet. That is what is the distance vector or the Bellman-Ford routing algorithm. It is distributed in nature, and this reflects any small change in the network globally, so that all the routers in the network can understand that, right. What is the strength of this algorithm? The strength is that a single change in the network can reach to the other nodes, and the neighbors can understand or can update their routing table if they understand the status of their neighbor correctly, right. This is a simple kind of network topology which can find the preferred path for routing of the packet. Let us see the drawback of this routing algorithm. We have a topology like this. Let us say we have a bus topology with 5 nodes A, B, C, D, E, let us say. There is a destination X here, and this is the receiver or any random destination, and initially the cost to the destination is unknown to all the nodes. So, what they do? They put an infinitive, that means the cost is unknown to them, and by some neighbor detecting technology, A understood that x is my immediate neighbor or next hop. So, I can reach to x with one hop, correct. This is in the first iteration, you can say. Rest remains as it is. So, when this value is exchanged, what happens to B? Now, B knows that A is my immediate neighbor and my neighbor can reach to x with a hop of 1. So, I can reach to x with a hop count of, correct. That means, if I can reach to A with 1 and if A can reach to x with 1, so my hop count is 2 to reach at x. This is in, and rest remains same. Next, this is in the second exchange, you can say, or second iteration. In the third stage, C understands that I can reach to B with 1 and B can reach to x with 2. So, I can reach to x with 3 because it is his neighbor. So, once this fellow updates, when he exchanges with his neighbor, the neighbor updates its table saying that I can reach to x with 3 counts, and this continues in the next 2, 3, 4 and infinity. This is in the fourth exchange and finally 1, 2, 3, 4, 5 in the fifth exchange. That means, in every iteration when the node exchanges its routing table, its immediate neighbor can update its table and they can find out the place, the cost to reach to any destination in the subnet. This is a very fair case, the best case scenario, right. Now, with this topology we will again continue, same A, B, C, D and E are there with the value that we found 1, 2, 3, 4, 5 to x, correct. Now, let us say the link between A and x is disconnected. The link between A and x is disconnected. So, what happens now when the exchange takes place? So, this becomes now, when the exchange takes place, A understands that my neighbor B can reach to x with a hop of 2. So, if I forward my packet to B, B can reach to x with a little knowledge that B has updated through him only, through 1, right. So, what he updates, he says with 3 hops I can reach to x. Once this is updated, now B says I can reach with a hop of 4. The reason is my neighbor is 3 and he can reach with 3 hops, my neighbor is 1 hop, he can reach with 3 hops, so I can reach with 4 hops. Make sense? Now, this fellow saying 3, 4, this fellow says I can reach with 5 because 1 hop to my neighbor and 4 hops to him, from him. So, 4 plus 1 is 5. So, this is how the 3, 4, 5, 6 and 5, and now it continues like. So, if this continues, finally you will see that the tables, the nodes, they are just updating their values, but none of them are able to connect to x. The reason behind is the actual connection between A to x has been disconnected, but they are only updating the routing table saying that we can reach up to, reflecting the updation to their neighbors that I can reach to that with this many number of hops. And this is a typical problem of distance vector algorithm called the count to infinity problem. This is a very typical problem. Why this problem occurs in distance vector and how this could be eliminated? So, the subsequent routing algorithms, when they faced distance vector to be one of the best algorithm who reflects the local topology in a global way, so that everyone can update the network scenario, but there are certain situations when they face the problem of count to infinity, and this problem was further eliminated by the subsequent routing protocols, and how they have been eliminated we will see in the next class. Right? Any questions?